All right, after knowing about work, power, and energy, okay, we then proceed on to look at the main essence of this topic, and that is the conservation of energy. Okay, conservation of energy. Okay, you have gone through thermal fluids 1 before, if you remember. There is also a very similar topic on conservation of energy. So for that case, you are talking about heat and work, right, and enthalpy, things like that, right? So for this case, over here, it's slightly different, but the concept is the same. Okay, you will need to define two states. Okay, simply put, state 1 and state 2. So state 1 is usually your initial state lah. So remember your two states is the initial state and then the final state. Okay, so state 1 is usually before and state 2 is usually after, right? And what the conservation of energy says that they should be the same. The energy at this situation, at this point, should be the same as the energy at the end of the process, okay, at this point. So what is there? What is inside this state 1? Well, you have all your energies lah. So you have your KE, okay, translational, KE, rotational, potential energy, and spring energy. Okay, so these are all state 1 at the start, and then you have the translational, rotational, potential, and spring energy at the final state. Okay, so comparing between these two, they should be the same. Okay, so let's just look at illustration to get a better understanding. Let's look at tutorial 1. Okay, so first question of the tutorial. Okay, a mass is dropped vertically from rest onto a spring. Okay, so originally this mass is 1 meter above the spring. Okay, and then K is given, a spring constant K is given. So what is the compression when the mass comes to a complete stop, and what is the velocity when the mass just hits the spring? Okay, so these are the two parts. So you're gonna define the state 1 and state 2 first. Okay, you can start off with a mass. Okay, this mass is 0.5 kilo. Okay, and there's an elevation, there's a height there, and below it, right, there is a spring. Okay, which is 1 meter below. Okay, so you're gonna have a spring like this, and it is going to rest on a surface. Okay, so that's the situation. Then you drop, and it hits the spring, right? So part A comes to a complete stop. So where exactly is it? Okay, it must have dropped and then it must have compressed, right? Compress the spring until it stopped moving. Okay, V equals to 0. So at this point, it's just before the mass starts to bounce back, right? So you can draw something like that, and the object is here. Okay, just before it starts to bounce back. Okay, but at this point, right, it is at the lowest point. So what is the interesting feature here? Of course, the compression, right? So how much is the spring being compressed? We call this X. Okay, so state 1 and state 2. Where is the state 1? Okay, usually you will define it at the beginning. So this is state 1 at the beginning. State 2 is the point we're interested in, which is here. So this is state 2. Okay, then you look at the energies. Okay, state 1 equals to state 2. Okay, what energies do they have at 1 and 2? Okay, the first one, it is being released from rest, right? So there is no velocity, there is no KE. Okay, but there is a potential energy. Okay, the question is potential energy, the height, where do you calculate from? Okay, this is where we start to use the zero potential energy line. You want to define it first before you calculate. So it's always between the two states. Okay, so state 1, the height is here. State 2, the height is here. Okay, you want to specify one of them as the 0 PE line, okay, for your convenience. So let's say usually we will define the lower point lah. So at this height is your 0 potential energy. Okay, with you being defining this, your height is now for state 1 is now this value. This is your H. Okay, so PE1. Okay, is there any spring energy here? No, because at state 1 the spring has not been compressed yet, right? So there's only PE1 for state 1. State 2, okay, is there any potential energy? No, because we already defined at this height the mass does not have any PE, right? So there is only compression energy here, okay, spring energy here. Okay, so PE1 is mgh, right? So mg, so what is h? The h value will be 1 plus x, okay? And then this one will be kx. No, not kx, half kx squared, sorry. Spring energy is half kx squared. Okay, so you should be able to get, this is the k is 300, so this is 150x squared. So it turns out to be a quadratic equation. Okay, you should be able to express this equation into this 905 equals to 0. Okay, then you press your calculator, you find the root of x. So the root where 0.1979 meters is the answer. So the spring is being compressed by 0.1979. Okay. Okay. Part B. We are now concerned with the point where the spring, the mass, just hit the spring. Okay, just hit the spring. So let me draw it again. This is your mass, this is my spring. Just hit the spring is here. Okay, just hit the spring. So this is 1 meter. So this would be your state 1 and this would be your state 2. Okay, at this point before it touches the spring, the object still has a velocity. Okay, but the spring does not have any compression. So state 2, there is no spring energy now. Okay, and it's between these two heights. Which one should we define as the 0 potential? Okay, always take the lower one. So this will be your 0 PE elevation, 0 PE line. Okay, so again state 1 equals to state 2. State 1 again only has potential, right? And how much potential? mgh, which is 1. Okay, state 2 now it does not have any spring energy already, because both states the spring is not compressed. Okay, so this one only has a kinetic energy. Okay, half mv squared. Alright, so both sides there's a mass, I can cancel it away. So my v is basically root 2g. Okay, my v is basically root 2g, which is 4.43 meter per second. Okay, so again important to define which are the two states, to define your 0 potential energy, and the rest you will be able to express into the equation.